Hi, everyone. In order to explain the stability of aromatic compounds, we need to invoke MO theory. So molecular orbital theory tells me that when two atoms come together to form a bond, they form an antibonding orbital and a bonding orbital. The anti-bonding orbital being higher in energy and the bonding orbital being lower in energy than the two individual atomic orbitals. In the bonding orbital where there is constructive overlap, and in the antibonding orbital where there is destructive overlap. And so there is a node in the middle of those orbitals. Now, when we look at ethene, that's C2H4, we have a sigma bond and a pi bond. And for these MO diagrams, we're going to be looking at the pi molecular orbitals. Okay? So if we consider just the pi MOs here, we're talking about two atomic p orbitals, each having an electron, coming together to form two molecular orbitals, right? The number of orbitals is conserved. We're starting with two atomic orbitals. We're going to make two molecular orbitals, a bonding and an antibonding. And the antibonding is going to be denoted by a star. So this is a pi star orbital, meaning a pi antibonding orbital, and then a pi bonding orbital, just pi. So what do these orbitals look like? Well, these p orbitals in the bonding orbital will be in phase, right? These will be able to overlap to form a cloud of electron density above and below the bonding axis. And so this is typically what we see there. Now the antibonding orbital will be mismatched, meaning that there will not be orbital overlap here. And this will be, of course, higher in energy, and this contains a node. The number of nodes in an orbital is equal to n minus 1. So if this is the second orbital, we would have 2 minus 1, 1 node, and this has 1 node. We fill the orbitals from the bottom up, just as we do for any other orbital, following the Aufbau principle and then spin pairing. So this would be the highest occupied molecular orbital, and the antibonding would be the lowest unoccupied molecular orbital. Now let's look at a slightly more complex example. Let's say we have 1,3-butadiene. Okay, I'm going to just move this up higher so I have more space to work. Here I have 4 p orbitals, and these are all on adjacent atoms, so all 4 of these p atomic orbitals can interact to form 4 atomic or molecular orbitals. So I'm going to have my 4p orbitals, and they're going to form 4 molecular orbitals, 2 bonding that are lower in energy, and 2 antibonding that are higher in energy. So when we start to think about what these look like, you can start from the bottom. This is one of the easiest ones to draw because all of the orbitals in the lowest energy orbital will be aligned. Okay, so we have this continuous overlap of electron clouds above and below. As we increase in energy, we increase the number of nodes, which is where there is a switch in the phase of the orbitals. And these will always be symmetrical. So the easiest way to do this is split it down the middle. That's your 1 node. You have these 2 orbitals in phase and these 2 orbitals in phase. And that is where you get the picture of the isolated double bonds, right? Here's a double bond, and here's another double bond. As we go to the 3rd molecular orbital, we're going to have 2 nodes, and symmetrically placing these nodes would have to be as such. So we will fill in the shading on the first one, switch to the bottom, and then switch again. And the highest energy one is also another relatively easy one to draw because the number of nodes will be such that we alternate the phasing on each orbital. So the fourth molecular orbital would have n minus 1 nodes. That would be 3. And everything is alternating in terms of the phasing there. So we fill according to the rules. We get a HOMO here and a LUMO up here. So you can kind of tell from my orbital diagram that the bonding orbital for butadiene is lower than the bonding orbital for just ethene. And this is due to the delocalization of those electrons, right? They have a larger space to occupy, and they are therefore more stable, lower in energy. And this plays into the reactivity of these so-called conjugated systems. When we have alternating single, double bonds, we call that conjugation, and it leads to stability. So looking ahead, I would like you all to try the molecular orbital diagram for 1, 3, 5 hexatriene. This would have 6 p orbitals, so 6 pi molecular orbitals, and just follow the protocol that I did for 1, 3 butadiene and see if you can come up with those unique patterns there, okay? So if you have any questions about this, please let me know. I would be more than happy to address them for you, and I will see you soon. Thanks for watching.